So today I would like to explain about shear forces and bending moments. So here what is the shear force? Shear force is the vertical imbalance force in any particular structure. So a structure may be subjected to number of loading. For example, if I take a particular cantilever beam, maybe it is subjected to some loads here acting like this. Okay. Then what happened? At any section, if you consider the vertical imbalance force, total forces means the sum of downward forces and the sum of upward reactions. While I am adding, I am going to get 0. These two are equal always here. But whenever if you consider any section here, whatever the unbalanced force left side of the section what we have, and similarly the unbalanced force right side what we have is always equal, and the imbalance force is what is called as shear force. So the sign conventions. In shear forces, the vertical left side upward force and right side downward force will be always causing positive shear, and similarly left side downwards and right side upward force will be always causing negative shear. So whenever we draw the shear force diagram, these sign conventions must be considered here. So based on the direction of the external force, we can give the either positive shear or negative shear. Similarly, while I am talking about the bending moments here, what is bending moment? Bending moment, it is nothing but the algebraic sum of the moments. What is first moment? So before discussing about bending moment, we should know about a moment. Moment is nothing but the product of force and the perpendicular distance. Whenever any structure is subjected to loading, at any section if at all I want to calculate the moment here, at that particular point the moment is equal to load into the perpendicular distance. Okay. For example, if I consider a cantilever beam, if there is a point load acting here where the intensity of this point load is equal to 10 kilonewtons and if the distance is 2 meters, then the moment at this particular point A is 10 into 2. So moment at A is equal to 10 into 2. So this is 20 kilonewton meter. This is the moment. But what is bending moment? Suppose if I have another force acting here in this direction, maybe this may be around 6 kilonewtons, and if the distance is 1 meter, then this 10 kilonewtons will give you some moment. 6 kilonewtons will also give some moment. Therefore, the bending moment at A is equal to the moment due to 10 is 10 into 2. The moment due to 6 into 1. Therefore, that is equal to 14 kilonewton meter. So this is what is called as bending moment. So moment is nothing but force into perpendicular distance. That is called a moment. Bending moment is nothing but algebraic sum of all the moments is called as bending moment. So while you are drawing the bending moment diagram, again we require the sign conventions. Whenever we draw any diagram, maybe shear force diagram or bending moment diagram, we require sign conventions here to avoid the mistakes in the drawing the diagrams. For example, while I am drawing the sign conventions for the bending moment diagram, if the beam gets sagging shape, then the corresponding bending moment will be positive bending moment. So if the beam deflects in the hogging direction, then that moment will be negative bending moment. So how you get the sagging or hogging here based on the direction of the load? Suppose if you consider this beam here, the 10 kilonewtons load is going to bend the beam to get the hogging direction. It is going to be bent like this because of this load. Similarly, because of this load, it is going to bend like this. So how actually the load is going to push the beam such that the beam gets the shape, maybe sagging or hogging. Based on that, we will have the sign conventions for the bending moments. So the drawing of shear force diagram, bending moment diagram are very, very important in the structural analysis point of view. Why? Because while you are doing the design for any component, maybe beam or a column or a frame, when we do the design of the element here, we require the bending moment values. So after having some knowledge about the shear force as well as the bending moments here, now we will explain here. I will explain how to draw the shear force diagram for a particular case here. For example, if I have a cantilever beam subjected to a point load downwards here, which is 10 kilonewtons, actually at a distance of 2 meters from the fixed support. Now let us assume that this is a cantilever beam subjected to that particular point load. Now if you ask me to draw the shear force and bending moment diagrams here, so let us calculate first the shear force at A. Similarly, shear force at B. There are 2 points here, starting point and end point. And before that, let us calculate the reaction here. What will be the reaction here? The reaction is equal to 10 kilonewtons only. So, because the entire beam is subjected to only one load, and the entire beam is having only single support. That is why the total load has to be taken care by this support only. Therefore, the reaction at A is equal to the external applied load. Therefore, the reaction at A is equal to 10 kilonewtons. But what about the shear force at A? Shear force at A is equal to RA, because left side upwards will be always causing positive shear forces. So, as this reaction is upwards, which is left side of the beam, that is why the shear force at A is equal to positive 10 kilonewtons. Similarly, the shear force at B is equal to the whatever the force acting here, that is called 10 kilonewtons, that is right side downwards. As this force is acting right side downwards to the beam, then the shear force will also be positive. So both shear force at A and shear force at B both are equal to 10 kilonewtons. Therefore, the shear force diagram is going to be a rectangle with 10 kilonewtons and 2 meters is the length. So this is the shear force diagram for this particular case. Similarly, if you ask me to draw the bending moment diagram here, first let us calculate the moment at B. Moment at B is equal to 0. Why the moment at B is 0? Because the point B is extreme free end. At extreme free end of a cantilever beam, the bend will be always 0. Therefore, the load is also acting here. Moment at B is always 0 because it is extreme free end. Similarly, bending moment at A, while I am calculating moment at A here, the beam is subjected to only one load. Therefore, the moment at A is equal to 10 into 2 is equal to 20 kilonewtons per meter. Whether this 20 is positive or negative, we need to follow the sign convention. While I am applying the load here, how the beam is going to get deflected? The beam will be deflected like this, because the load is acting downwards. The girder will also be deflected like this. Therefore, and you are having the hogging shape. The beam will be deflected with respect to this load in the hogging manner, and hence the moment caused by this load is going to be negative. Therefore, this is minus 20 kilonewton. Therefore, the moment at B is 0, moment at A is minus 20. Therefore, the bending moment diagram is going to be, you can show the bending moment diagram here. The bending moment is going at B is 0, A is 20. Therefore, this is the bending moment diagram. Bending moment diagram is going to be a right angle triangle here. So, this is 2 meters and this is 20 kilonewton meter. This is B meter. Okay. And this is S. Likewise, we can easily draw the shear force diagram and bend moment diagram here once if you know the sign conventions. So let us take another example. For example, now here I will just take another one where if I have a simply supported beam, for example, if you take here, it is a simply supported beam, because in our civil engineering we are having only 2 definite beams. One is the cantilever beam is a definite beam where the degree of redness is 0. The second beam is a simply supported beam, which is also a definite beam. So now let us consider a simply supported beam which is a definite subjected to some external load we give here. Mostly let us just have a UDL, let us give here, where the intensity of this particular load is equal to some 6 kilonewton per meter, where the span is equal to some 4 meters. Let us assume like this here. Then if you ask me to draw both the shear force diagram and bend moment diagram for a particular case here, so the first step must be always calculation of reactions. Calculation of reactions. Okay, this is the first step here. So we will have here 2 reactions. One is the reaction at A, the other one is the reaction at B, because the beam is supported by 2 supports. So you have reactions at both the supports. So how to calculate the reactions at A and reaction at B? Because usually to calculate the reaction at A, I should take moment support when equal to 0, because the bending moment at both the supports will be 0, because it is a simply supported beam where the moments are 0 here. In addition to that, as this particular beam is perfectly a symmetric beam, with respect to supports it is symmetric, with respect to load it is symmetric, with respect to geometry also it is symmetric, and hence the total load is equally distributed to both the supports, and hence the reaction at A and reaction at B both are equivalent to total load divided by 2. What is the total load here? 6 into 4. It is the total load. Per meters it is 6 kilonewtons. Per 4 meters it is 24 kilonewtons. And the reaction at A and reaction at B both are equivalent to half of the total load. That's why it is equal to 12 kilonewtons. So the reaction at A and reaction at B is equal to 12 kilonewtons. Now the shear force at A is equal to reaction at A. Why the shear force at A is equal to reaction? Because it is at end here, end point. At end point, what is the reaction I have here? That is going to shear force. As it is left side upwards, it is going to be positive shear force. Therefore, that is plus 12 kilonewtons. Similarly, shear force at B. Shear force at B is equal to reaction at B. That is also end point. But right side upward reaction. Right side upward reaction will be negative shear force. Therefore, shear force at B is minus 12 kilonewtons. Shear force at A is plus 12 kilonewtons. And hence, the shear force diagram is going to be like this here. So here at B I have minus 12. At A I have plus 12. Okay. This is the variation of this. Okay. So now this is positive shear force and this is the negative shear force. And this length is 2 meters. This length is also 2 meters. And exactly this point where the shear force is 0, where you can expect the maximum bending moment. So as per the regulations here, wherever the shear force gets 0, there you can expect the maximum bending moment. So now this is the shear force diagram. Similarly, now I will explain how to draw the bend moment diagram for the same case also. So while I am drawing the bend moment diagram for the same B, so let us calculate the bending moments here. First one, the bending moment at A, bending moment at B, both are equal to 0. Why bending moments are 0 at both the supports here? Because it is simply supported beam, where you will have hinge and roller supports. Extreme hinge, extreme roller will always carry 0 moments, and hence the moments at A and B are always 0. And let us look at a center point C here, such that the bending moment at center, let us calculate. So how to calculate the bending moment at center? Let us calculate now here. See, while I am calculating the moment at C here, you can start either from the left side of the gutter or you can start from the right side of the gutter. If I start from the left side, how many forces I have? One is the reaction, the other one is the UDL. So these two are the forces. This reaction will give some moment at C. This UDL will also give some moment at C. By adding those two moments algebraically, I will get the bend moment at C. Therefore, bend moment at C is equal to 2 into RA. RA into 2. That is the moment at C due to RA. That is going to be positive. Why this moment caused by RA is positive? RA is going to push the beam like this. Therefore, you get the sagging shape. Next one, the moment due to UDL. UDL is going to push the beam like this. Therefore, the moment caused by UDL will be negative. The moment caused by reaction is going to be positive. So this moment is positive, and the moment due to UDL. What is the moment due to UDL? 6 km per meter. So 6 into 2, that is the load. And the resultant load is always assumed to be acting as a centroid. So centroid will be exactly at center here, and hence this distance is going to be 1 meter. Therefore, this is the load and this is the distance. So this is the moment due to reaction, this is the moment due to UDL. Now let us substitute the value of RA. What is the value of RA here? Well, so 2 into 12 minus 12. Therefore, the answer is 12 kilonewton meter. So the bending moment at C is 12. The bending moment at A is 0. The bending moment at B is also 0. Now let us see how to draw the bending moment diagram for the same beam here. This is point A and this is point B, where the bending moment is 0 here, MA is 0, MB is 0, and C is the center point. At C, what is the moment here? I got 12 kilonewton meter. Okay. So MA is 0, MB is 0, MC is equal to 12. That is positive 12. If it is negative 12, I can show below the line. As it is positive means I have shown above the line here. Now let us connect the 3 points here. This we can connect it. While I am connecting them, we need to follow the sign conventions. Whenever the beam is subjected to UDL, the bending moment diagram is going to be a parabola. It is going to be a parabola plane. Okay. So this is parabola. Now it is a bending moment diagram. Similarly, when the beam is subjected to uniformly varying load, then the bending moment diagram will be cubic parabola. So we will have some characteristics of the bending moment diagram. So let us discuss about the characteristics also. At the point where the shear force is 0, at the same point I can expect the maximum bending moment. That is the first one. Second one, whenever there is a point load, whenever there is a reaction or a point load, there the shear force will be always vertical. Okay? Wherever there is a reaction, there the shear force is going to be vertical. Wherever there is a UDL, the shear force diagram will be linear. Wherever there is a UDL, the bending moment diagram is going to be parabola. So likewise, they are the important characteristics of the shear force as well as the bending moment.